All right, these notes are an introduction to vectors. So we're just going to talk about some of the basics of vectors, some of the beginning vocabulary, and start looking at how to find them and that sort of thing. So the definition of a vector is a directed line segment. So what this means is that it has a direction and a magnitude. And a magnitude is another word for length. But it does not have a location. So that means that we can draw a vector on a coordinate plane, but it doesn't have to be located at a specific spot on the coordinate plane. We're more concerned with the angle that it makes with the positive x-axis and the length of it. Those are the two things that we find to be important. So vector PQ, and this is how we write vectors. Typically when we write them, we show this little line segment with an arrow on the top. You might see some people who put both parts of the arrow, top and bottom. Either way is fine. Books sometimes put vectors in bold instead of having that line across the top, but typically when we write it out, instead of trying to write our letters over and over and make them bold, we typically write it this way. So vector PQ looks like this, where it has one point that you begin with, and this is called the tip of the vector. And then it goes to another point where the arrow is, and that's called the tail of the vector. And the tip of the vector is the initial point. Like I said, that's where we start. And so in vector PQ, this would be point P. And then the final point Q would be the terminal point. Right? So that's how we write vector PQ. Then if we put two lines, kind of like you're saying absolute value, but it's not. When you write the two lines like this, this is the magnitude, or the length, from P to Q. All right, there are two types of notation for vectors. One is called component form. That's what we're going to work on today. Tomorrow we'll be working with the linear combination form, which is AI plus BJ, and we'll learn about that tomorrow. So today for the component form, we're going to say that our initial point is x1, y1, and we'll go ahead and draw that initial point. And we'll have a terminal point, x2, y2. And then we'll say that the vector v, if we want to call that overall vector v, that's going to be x2 minus x1, y2 minus y1. So whenever we do this, we're always going to do the end point or the terminal point minus the initial point. So terminal point minus initial. All right, and it's going to kind of look like it's written as an x coordinate and a y coordinate, but it's not. It's written as the difference in the x's and the difference in the y's, which means that when we get our resulting vector, we have v1 in the first position, which is considered the horizontal component of the vector, and v2, which is considered the vertical component of the vector. So what that means is that even if you're tempted to relate a vector back to a point, an x and a y point, it's actually more similar to a slope, where this is like the rise and this is like the run. All right, so we're going to go ahead and write one more type of formula, in this component form, and that is how to find the magnitude of vector v. And to find the magnitude, we use the the distance formula, which is x2 minus x1 squared plus y2 minus y1 squared. So you would use this formula if you had two different points, like if you were saying here's the vector, it comes between these two different points, find the magnitude of it, then you can just find the distance between the 2 points. Or if they have given you a vector already written as a horizontal component and a vertical component, then you can say that's just the square root of v1 squared plus v2 squared. All right, so we're going to go ahead and do an example of the stuff that we just talked about. So we're going to say find the direction and magnitude of vector rs given that point R is -2, 5, and point S is 2, -8. Okay, I went ahead and put a little grid on here so I can draw this. You can draw a sketch on your notes. So here's the point -2, 5, that's point R, the initial point R. Then the point 2, -8 is down here, that's the terminal point S. So that means that this vector looks like this. Oop, almost a straight line. Okay, and so to find the components, the component form of the vector, we always do terminal point minus initial point. So vector RS is going to be 2 minus -2, -8 minus 5. So you can see I did the second one minus the first one, the second one minus the first one. So that gives me a horizontal component of 4 and a vertical component of -13. And if you look at this, this vector goes to the right 4 and down 13. So like I said, it's less about x and y coordinates and it's more about slope. To the right 4 and down 13. All right, so now if we wanted to find the magnitude of RS, we would take the square root of 4 squared plus -13 squared, which is the square root of 16 plus 169, I believe, which is the square root of 185. And we could probably simplify that. 20, 16, 17, oh, maybe not. It looks like this is, I should get a calculator and double check. I believe that is 5 times like 27, 20, 17, 37, something like that. 185 divided by 5 is 37. That's 5 times 37. And I believe 37 is a prime number. I can't remember. But either way, we can't simplify that square root. So we're okay with saying that the magnitude is just that. So if you can, you should be simplifying square roots as we go throughout this unit. Okay, so next we're going to go ahead and talk about equivalent vectors. So two vectors are equivalent if they have the same direction and magnitude. So basically, if you take the two different points, the initial point and the terminal point, and you write the vector from it and your component form is the same, then they're equivalent vectors. So anytime I give you instructions and I say find, write the line segment in terms of its direction or magnitude, that's saying write the vector. So the reminder here is that the location does not matter. So it doesn't matter where the terminal point is, where the initial point is, none of that matters as long as the component form is written the same. So remember that location does not matter. All right. So for example, we're going to show that vector RS equals vector OP given that R is 7, -3, and S is 4, -5. O is 0, 0. P is -3, -2. And so to do this, we have to write the vector in component form from the direction and the magnitude, and then we have to find the magnitude and just verify that they're the same. And these points will, or these problems will feel a little bit frustrating because it's kind of like, duh, they're the same. But the definition of equivalent vectors say we have to prove using both of these ideas of the definition. So even if it feels redundant, you do have to go through the process twice. So we're going to go ahead and find vector RS. And so we do, this is the initial point, this is the terminal point. So I'm going to say 4 minus 7, -5 minus -3. So just to clarify, you notice that the initial point is always the letter that comes first. The terminal point is always the one that comes second. So vector OP would be -3 minus 0, -2 minus 0. And so that means that RS, 4 minus 7 is -3, minus minus makes a plus, so -5 plus 3 is -2, OP is -3, -2. So at this point, we already know that the magnitude is going to be the same because we know the formula for magnitude is just to square that and add them together. However, the definition says show that everything is the same. So even though we already know that they're equivalent vectors, we do have to keep going. So here I'm going to say check, check, so the component form is the same. Now I'm going to find the magnitude of RS, which is the square root of -3 squared plus -2 squared. The magnitude of OP, which again is the square root of -3 squared plus the square root of -2 squared. So 9 plus 4 is the square root of 13. And square root of 13, and check, check. So now I can say they are equivalent vectors. Because they have the same magnitude and direction. So I know that this part of the video probably feels a little bit frustrating because it seems unnecessary, but we're starting to move into more formalized math where we have to be proper and say if we're going to prove something is true, then we have to check all of our boxes and write our conclusions and do all that sort of thing. So this idea right here that we're doing of jumping through some hoops to prove something is pretty common for what we'll eventually experience when we take calculus. Okay, so one last thing that I want to talk to you about is vector operations. So that means adding and subtracting vectors or multiplying or whatever. How to do that. And there's actually two different ways of doing it. One is algebraically, so that's just doing it completely on paper. The other way is geometrically, and that means that you're doing it visually. So I'm going to explain to you how to do both ways, and then we'll probably have to practice them a little bit more in class tomorrow. So the first way is algebraically. So we're going to start off saying that vector u is defined as u1, comma u2. Vector v is v1, comma v2. And so we have a couple formulas here that you can think about, and I'm not going to make an exhaustive list, I'm just going to kind of show you how it works. So vector u plus vector v is the horizontal components added, and then the vertical components added. And this, whenever you're taking two vectors and adding them together, the result that you get is called the resultant. So they will often talk about the resultant vector when you're done with an operation. We can also have something called scalar multiplication. So if I have k, some sort of constant, multiplied by vector u, then it's going to be k times as long as vector u. So if this was 2 times u, then that vector would be twice as long as normal. If it was 1/2 u, it would be half as long as normal. So here we would just do k times the horizontal component, k times the vertical component, and then that would be the resultant vector. Okay, so for example, if we had u is -3, 7, and v is 1, -2, then u plus v would be -3 plus 1, and 7 plus -2. So that would be -2, 5. Okay. Or we can do that scalar multiplication there. So if I wanted 5 times u, that would be 5 times -3, 5 times 7, and so that vector would be -15, 35. And we can do all sorts of different combinations of this. We can do 3u minus 2v. We can do u minus v plus another vector w. There's all sorts of stuff you can do with that, but it works out about the way you would kind of expect it to. So I think algebraically is pretty easy to work with. All right, what is a little bit more difficult to work with is adding vectors or subtracting vectors or whatever, doing it geometrically. So what we're going to do is we're going to write down the instructions, and I'm going to show you one, but then I'll leave the rest for class because I think this is something that might be better in person, so you can ask questions and I can explain things. Okay, so if we were completing the problem vector u plus vector v, then the first thing we would do is we would draw vector u. And you can do this on a coordinate axis, but you don't have to. You can just draw it on a white sheet of paper as well, just making sure that you're being consistent with that idea of like, oh, it goes left 4 and up 3 or something like that. Okay, next, you're going to draw v where the tip of v, so the initial point of v, connects to the tail of u. So that means that u ended at an arrow, and so v starts at that arrow to continue the picture. Okay, so draw v where the tip of v connects to the tail of u. Because of this, when we do our drawings, so we're adding things geometrically, we keep in mind tip to tail. It helps us remember how to go through and add and subtract. All right, and then step 3 is to draw the resultant vector from the tip of u to the tail of v. Okay, so draw the resultant vector from the tip of u to the tail of v. All right, so if I'm going to draw the problem that we did before. So you'll need to get out a different sheet of paper. I'm going to go ahead and draw it on here. So if I go back to what vector u was, that was negative 3, 7. So I'm going to go ahead and start here and go left 3 and up 7. So here is vector u. So there's the tip of u, there's the tail of u. Then from here, I draw vector v. And vector v was right 1, down 2. So I'm going to go to the right 1. Ooh, that's a terrible one to draw. Maybe I'm not going to draw it. I'm going to make up a new problem. Well, okay, I'm going to go ahead and keep this. I'm sorry, we could have done that problem, but it would have been hard to be able to see. So I'm going to say, we're going to make up a new problem, so I'm going to say vector u is negative 3, 7. Vector v, I'm going to say is negative 4, negative 3. And we're going to go ahead and find u plus v. So that means from here, if I'm starting to draw vector v, I'm going to go left 4, down 3. So left 1, 2, 3, 4, down 1, 2, 3. So there's vector v right there. So this is u plus v. And then to draw my resultant, I start at the, so I did tip to tail here. Now I'm going to do tip to tail here. So tip to tail here. And this one right here is u plus v. So that's 1, 2, 3, 4, 5, 6, 7. It went left 7, and then up 1, 2, 3, 4. Up 4. And if you look at what our result should have been, then when we add the horizontal components together, we do get negative 7. When we add the vertical components together, we do get 4. So it's the exact same thing as adding and subtracting algebraically. You're just doing it visually instead.